and my invention is thermal dynamic processes of rejecting and transferring heat. Rejecting, storing, and transfer of heat.
Okay, so I've just been asking some questions about how does this compare to present-day technologies. In a nutshell, can you go through that again?
In a nutshell, this is a combined system where instead of a furnace attached to an air handler and a condensing unit, an outdoor condensing unit outside of the building attached to the air handler, this system uses the same refrigeration cycle, except it puts a phase change material around both coils has a definable phase change that we can pick at 1 degree increments. So we've got a very low phase change on our cold side around the evaporation coil, and a very high phase change point around our condenser coil. What that does is it actually makes the efficiency of the thermal energy being rejected or added to the tempered environment, the air that's in a building, not as drastic of a change to the fins of the of the condensing unit or the furnace. So it's kind of a moderator in between, and it drastically cuts it to the point where nobody would believe if we said it was 99.9% more efficient, but it is.
So again, that question: why are not people lining up at your door?
Well, first of all, we had to we developed this. This was developed in 2011. Actually 2010. Wrote the patents. Got a Jones Day pulled in, came in as our new patent attorneys. They said stop everything. Built a lot of fences around it, because this not only applies to heating and cooling, but it also applies to getting water out of the atmosphere. As far out there is protecting spent nuclear fuel rods. The storing of thermal energy is a very broad application. So they basically went from 8 claims in my patents now to 159 claims, and separated into 2 patents. So we got that basically all published internationally. They've been granting internationally now. They gave us the green light to go forward.
Are they still pending, or are they?
They're granted in numerous countries. Okay. They're pending still.
These are international patents?
International.
Oh, okay. Yeah. All right, excellent. Excellent.
And so, they're utility patents.
So let's go over that energy input-output in comparison with systems today again.
Okay, so this system, this is the last prototype before we go to manufacturing. Our manufacturer is a Malcolm Baldrige award-winning manufacturer out of Dallas, Texas. We wanted to run all the tests first on our last prototype before we basically said, okay, start manufacturing. So we've just given them the thumbs up, the green light to go forward with it. But this replaces a 5-ton unit. Uses 100, right now you can see it's 100.
Okay, how many ton? Well, it's not even a ton. So what is this?
So a 5-ton unit basically is 60,000 BTUs per hour.
Yeah.
And the way they measure that is they look at the CFM of a fan, of the blower, which is part of every system. So we used a typical blower fan for an air conditioning and furnace, air handler. This is 1600 CFM. They then take the air going in, the temperature of the air going in versus the temperature of the air coming out. They want to see a 20-degree difference. That times the CFM times 1.085 gives you a certain amount of BTU hours. In the case of a 5-ton air conditioning unit, that's 60,000 BTU hours. It uses about 7.5 kilowatts of power to do that job. Ours does more.
So how much do you save in the contractor or the developer?
Well, you're basically going from 7.5 kilowatts per hour, running about 13 hours a day, to running 118 to 120 watts about 2 to 3 hours a day. Because we're not cooling or heating our phase change materials at the time that we're actually blowing the air through. We don't need to. We've stored that energy.
Okay.
Right? We've actually stored that energy and built thermal walls at those phase change points. In the cold side, below negative 15 C. On the hot side, above 48 degrees C. So our hot side gets up to 70 degrees C, which is 158 degrees Fahrenheit.
Yeah.
Way hotter than you'd ever want your home. Same thing with the cold side. We're below negative 18 at all times. So you always have a large mass to reject the heat of the atmosphere into, and as you reject it, as your room cools down or heats up, less and less thermal energy is being transferred, which means the old style type of systems just way overkill.
Yeah.
I mean, really, you're talking about 60,000 BTUs per hour in a month to do a 2,000 square foot house.
Right. This is what I want to hear.
It's like having an iceberg bigger than the house. That's the amount of that's how much cooling you're doing. They're very efficient in cooling. They're just terribly inefficient in rejecting it out of the atmosphere of the home. Because air is a slow cycle. This is the refrigeration cycle is a brilliant cycle. It's very efficient, but it's very rapid. So this is kind of puts a moderator in between.
Okay, so in Florida, the average cost to run the air conditioner, I know because I have a house in Florida, is about $200 if you're running it all the time. So what do you think this baby could do? A version of this baby?
A monthly cost of this for a 2,000 square foot house?
Yeah.
$5 a month.
Well, that's just incredible. Tell me a little bit about the refrigerant. You said
the refrigerant is the standard R134A. We're using 4 ounces.
Hello.
That's it, 4 ounces of it. Our pressure is at 5 PSI. That's all we need. You can see, since you've been here.
You're running this thing right now.
Yep, it's running right now.
Okay.
There's our hot side and our cold side.
I wasn't sure because it's so damn quiet.
Right.
Tell me about why it's so quiet.
Well, actually, that's the fan. If I turn it off, you can't hear anything. There's under 5 dB.
That's incredibly quiet.
There's if you look down the side of it, actually, let's pull this over here. If you look down and try to hear, you can hear. We're using a standard compressor.
Yeah, I see that.
And that's running. You actually have to touch it. And most compressors you can't touch, you'll burn your hand.
So it should last a lot longer.
Yeah, this will last. We don't know how long it will last because we're well below the ratings or for the compressor's requirements. So when we called the application engineers at Embraco, who makes this one, they said, "Shoot, you far surpass our lifetime warranty." So because we're barely running it, we're not putting it under a lot of stress. Our gap between the two, the condensation coil and the evaporation coil is one's at above, say it's 60 degrees C, the other one's down below 20 degrees C. That's a large thermal gap, right? So the compressor is really not working to maintain that because it takes a lot of thermal energy to break that phase change, right? There's all that latent heat, and our phase change material, just like water, has like close to 300 joules per gram. These phase change materials that we're using are definable, and they're high joules per gram, over 250 to 270 joules per gram. Each one's a little bit different, but they're definable. So depending on where we're doing it, if we're going to be doing this in Alaska, we just ship it with different phase change material for that environment at the 2 different levels. Now, the other thing we can do is we also have patented ways to actually change that phase change point in the tanks by adding pressure or reducing pressure in that tank.
So you're basic modus operandi is to go in and do a feasibility study and kind of custom design these for each.
We already have people that want to order these and just put them in their buildings. A few in Dallas. Our manufacturer has hundreds of thousands of square feet of manufacturing. He can't. Buildings like this is 8,000 square feet with high ceilings. Right. So you don't air condition them.
No.
No, but you die in the summer here, right? And in the winter, we're all wearing coats because it's too damn cold. So this is designed for a 2,000 square foot space. So obviously it's too small.
All right, so you can switch it over and produce heat.
Yeah, so it produces heat.
Okay. Can I go around the back and feel the cold air coming out?
Yeah, that's the air going in.
That's
and actually,
where's the air going out?
Well, if we want air going out, we do this. We'll open up the vent.
Yeah.
And turn this on. And
yeah, that's nice. That's pretty damn good.
Yeah, and this is not fully charged.
Yeah.
When it's fully charged, it looks like it's this full. And this one, that's it. If you look down inside this, that's completely iced up. That's because this is at negative 32 degrees C. I can put the meter on it so you can actually see the. Let's pull this meter off here and let's bring it over to this one. It was negative 31 degrees C, running at 110 watts, and the hot side's is 32 or 33 degrees C. So we've got a nice big thermal difference in a space. So we've got PCM tanks that encase our evaporation coil and the condensing coil. Again, it's just instead of taking that thermal energy and letting it go to waste, we move it where we want it and we store it. So it's conservation of energy.
Well, yeah, well that's advisable. Or you could make electricity out of it, couldn't you? Between the hot side and the cold side.
Well, we do have. If you saw in here, you saw some of these fins.
Yeah.
If you look down inside, you see those fins.
Yeah.
There's thermoelectrics that connect to the cold side and to the hot side. So cold side to ambient, it's making electricity. Hot side to ambient, it's making electricity. Right. That's what's powering our.
So you're using it to power the unit.
I'm gonna have a leak somewhere, so I might as well make the best use of it. So
exactly. And it's direct. I mean, contained in the unit makes absolute sense.
So
Can you just very briefly tell me how you met Eddie Teller?
How I met Eddie Teller?
He's the one who told me about you guys.
I don't know who Eddie Teller is.
He's the one who told me that.
Nathan probably.
Oh yeah, Nathan knows it. Yeah.
Nathan knows.
Okay.
I met Nathan about 2 months ago. He was working here. Actually, knew Tim, who owns the shop. We kind of call it a do tank instead of a think tank. We actually build stuff.
Well, I like that. I like that.
And
get it out there.
We've got
how long would it take you to get scale up in manufacturing?
Off because it's freezing my ass.
Yeah. Okay. How long could it take? Can you do scale up in manufacturing?
They're pricing it out, all the parts right now, and we could go into the hundreds of units in about 4 months.
Really?
And thousands of units. It's a very simple build.
All in Dallas?
In
Dallas?
All in Dallas, yeah. Well, Garland. Yeah, Garland, Texas, which is just outside the suburbs.
Okay. What do you think the cost of this unit here is going to be?
Well, we're still debating how we're gonna do that. I mean, we've got a couple of large air conditioning companies coming in this week because this could be done. This changes the whole ballgame because the air conditioning industry is a $200 billion industry worldwide.
Of course.
That's mostly new construction and the units that broke down. This allows people that actually have no air conditioning to now have air conditioning is now affordable, and you don't have to rip apart your whole building. You're not running copper lines throughout your whole. This fits. This is not the finished one. This is actually a prototype. The finished one is there's 2 modules, about 14 inches by 14 inches by 6 inches deep, separated by the hose. The compressor sits in a small little box that is somewhere between the 2 of them.
So you just do localized
You could do localized up to
implementation.
2,000 square foot, right? So if it's if it's a commercial project, you can do a very large.
Interesting,
space, right?
That changes the game.
Totally changes the game. So now you're talking about that. Just open that market up to now the entire built environment. Who's not going to be looking at their electric bill going, $200 to $500 a month for 2,000 square feet versus 5? It's a no-brainer.
Okay, so did you hire bodyguards?
No. We actually took the patents, and the patents are actually in separate trusts, and the Royal Bank of Canada is our trustee.
So you're untouchable.
It's safe.
And if they try to take you out,
it doesn't matter. It's already protected. Yeah, we had the best legal.
I'm only half joking. All right, so
no, this is a benefit for everybody. I mean, it basically the whole industry should get a boon. I mean, it's really they're not.
Well, not the ones that are already like Rheem and what's the other one?
Why? They just changed their system out to this system. They're still, they're manufacturing instead of big, huge condensers that go outside that have all of the, the regulations.
So you're not interested in starting your own distribution company?
I'm an inventor. You know what? I mean, I have 150 other patents I want to get done.
Okay.
So what we're looking for is people that want to do distribution and license technology.
Let's talk about that.
To basically get it out quickly as possible, because air conditioning and heating, 70% of this country's energy needs. If we could, with one type of product, reduce 70% of our energy needs, we don't need to import oil. We don't need to have coal-fired plants.
We don't need to have wars.
Exactly. We just changed the whole system by basically taking something that was a very efficient cycle, which is, the refrigeration cycle, that just wasn't efficient in its final execution, right? That allows us to basically get off
oil,
distributed power, off oil.
So you solved the ISIS problem.
Plus, if you hook it up and in this setup where we're testing it, this prototype 2, not as an air conditioner, but an atmospheric water.
I want to talk about that.
That's why I've got an iceberg in there. I've purposely let it freeze for the last 2 weeks, just taking it inside a room. When we first built the first prototypes for that application in my home office in August, 110 degrees, 7% humidity, I was making snowballs in the summertime in the desert using this same system. So what we're trying to do is figure out in different humidities what the overall amount of water we get. We know
what's the quality of that water?
It's perfect. It's because we're not going from vapor to dew point liquid. This is brute force. That's negative 31 degrees C. So 0 C is water to water.
In other words, there's no contaminants really.
No, it's going through 2 phase change, 2 latent thermal energy standpoint. It goes from vapor to in microseconds to a solid, in an instant. So nothing holds on that strong. Particulates, grime. You see clouds form. So the cycle is very quick and very clean. So then it just gets scraped off the shell.
Well, we look forward to those modifications.
That's gonna...
But right now we've got this this basic unit, and we can get this moving. We can get sales going pretty quickly with this, with the right contract signings.
Yeah, basically what we're doing now is we're taking orders for our manufacturer, and they'll just drop ship out of their facility out of.
Yeah, this is absolutely fascinating. So just let's close off the discussion of this one. Anything else you want to say about it?
No, this is it. It's a very simple fix to a big problem.
Okay, another invention.
Well, we touched